Have you ever really thought about what happens when you flip a light switch? I mean, really thought about it. Today, we're going to follow the incredible journey of a single electron to see how that simple action unleashes the power that runs our entire world.
Right? Let's get into it. You flip a switch and boom, the light's on, instant. But inside that simple copper wire, there's a whole universe of activity, a story of total chaos and perfect order all at once. To really get it, we've got to zoom in and follow the particles that make it all happen, the electrons.
So, first things first, we throw around the word current all the time, right? But what does it actually mean? In the world of physics, it's a very, very specific idea.
And the key word here, the one you really need to remember, is rate. It's not just that electric charges are moving. What matters is how many charges are flowing past a certain point in a certain amount of time. That speed, that rate of flow, that's current.
Think of it this way. A slow trickle of water and a fire hose can both deliver the same total amount of water, right? But the fire hose has a much bigger impact because it's delivering it all at once. It's the exact same with electricity. A slow flow of charge doesn't do much, but delivering that same charge instantly, that's powerful. It is all about the rate.
And to measure this rate, we use a unit you've probably heard of, the ampere, or just amp. 1 amp is defined as 1 coulomb of charge zipping past a point every single second. Now, get this. A single coulomb is about 6.24 times quintillion electrons. That is a truly mind-boggling number of electrons flowing through your lamp cord right now.
Okay, so this is where we hit a really common point of confusion, one that trips up even science students. Which way is the current actually flowing? Well, believe it or not, the answer is kinda complicated.
Yeah, this slide gets right to the heart of a major historical mix-up. See, way back in the day, scientists like Ben Franklin just assumed that it was positive charges that were moving. So they defined conventional current as flowing from the positive terminal to the negative one. Makes sense. But they were wrong. We later discovered it's actually the negatively charged electrons doing all the moving, flowing from negative to positive. We call that electronic current. So why on earth do we still use the old, wrong way in circuit diagrams? Honestly, it's just tradition. It became the standard, and it stuck.
So if it's these electrons that are really on the move, what gets them going? And what does their journey actually look like inside that metal wire? Is it a nice, neat highway?
Well, without a battery or any power source, the inside of a wire is total, absolute chaos. You've got billions of free electrons just zipping around at insane speeds, bouncing off atoms like pinballs. But here's the thing. For every electron moving left, there's another moving right. They're going nowhere fast. The net flow is zero. And if there's no net flow, there's no current.
But the second you connect a battery, everything changes. The battery sets up an electric field inside that wire, and that field acts like a constant, gentle push. The electrons are still bouncing around like crazy, but now, on top of all that chaos, they're all being nudged, ever so slightly, in the same direction.
We call this average forward movement drift velocity. And here's the part that might blow your mind. It is incredibly, unbelievably slow. We're talking less than a millimeter per second. It's not a sprint. It's more like a very, very slow, coordinated shuffle.
You know, this idea of drift velocity is really just a brilliant simplification. It lets us totally ignore all that messy, chaotic bouncing around and focus only on the net movement that actually matters. By basically pretending that the electrons are all marching neatly in a line, we can build the math that perfectly explains how that tiny, slow shuffle creates the powerful currents we rely on every single day.
All right, now that we understand the electron's wacky journey, let's talk about the simple, elegant law that governs the whole thing, the rules of the road, if you will.
And that rule is Ohm's law. It's one of the most fundamental principles in all of electronics, and it beautifully connects the 3 main characters in any circuit: the push, the flow, and whatever's pushing back. V equals I times R. Simple as that.
This slide breaks it down perfectly with a great analogy, a water pipe. So voltage, that's the V, is the electrical push from the battery. Think of it like the water pressure in the pipe. Current, our old friend I, is the actual flow of the electrons, just like the amount of water flowing through the pipe. And resistance, R, well, that's anything that opposes the flow, making it harder for the electrons to move. It's like making the pipe narrower.
And resistance isn't just some abstract concept. It's a real physical property of the wire. For example, a longer wire has more resistance. There's just more stuff for the electrons to bump into. A thicker wire has less resistance because there's more room to flow. And of course, the material itself is a huge factor. Copper is an amazing conductor with very low resistance, which is why we use it for wires.
Okay, so let's connect all the dots. How does this microscopic, super slow drift of countless electrons translate into the massive amounts of energy that light up our homes and power our cities?
Well, the answer is electrical power. Power is the rate at which energy gets delivered. You can think of it as the amount of work the battery is doing to push those electrons, combined with how many electrons are actually flowing. The math is simple. Power equals the voltage times the current.
Now, this brings us to a huge, real-world engineering problem. We know every wire has some resistance, and that resistance makes the wire heat up, which wastes energy. So when power lines have to stretch for hundreds of miles from a power plant, how do we stop most of that energy from just bleeding off into the air as heat?
The solution is actually pretty genius, and it all comes back to the math. See, the amount of power you lose to heat is calculated by taking the current, squaring it, and then multiplying by the resistance. The key part is that the loss is tied to the square of the current. So if you can lower the current, you dramatically lower the power loss. To do that, power companies transmit electricity at incredibly high voltages. A super high voltage means you need a very tiny current to deliver the same amount of power.
And this chart just lays it out perfectly. By cranking the voltage way, way up, the current can be kept super low. And a tiny current means a massive, massive reduction in the power that gets wasted as heat. This is the secret to our entire electrical grid.
And just like that, we've come full circle. The instant you flip that switch, you are commanding this whole incredible process, from the chaotic dance of particles to a guided, orderly drift, all governed by the laws of physics and engineered to efficiently bring power right to your room.
But I'll leave you with one final thought to chew on. If the electrons themselves are moving slower than a snail, why does the light come on instantly? It's because the electric field, the signal telling all the electrons to start moving, travels down the wire at nearly the speed of light. Think of a long tube packed with marbles. You push one marble in one end, and another one pops out the other end almost instantly. Each marble only moved a tiny bit, but the effect was immediate. But digging into that? Well, that's a story for another explainer.